Okay, so this is the second component of the series on the wonderful world of molecular anions. We're now going to look at some examples of the kinds of things I was talking about earlier. So first of all, dipole-bound anions. Let's think about, suppose I came to you and I said, here's acetonitrile, and you're going to add an electron to that. Well, where's the electron going to go? I think most undergraduate students would say, well, these CN pi star orbitals are fairly low-lying, so I think you'll form an electron in one of these CN pi star orbitals. And that'd be the lowest state of this acetonitrile anion. Well, that's not true. These molecules here, they have large dipole moments, 4.3 debis, 4.6 debis. So actually, in molecules like this with very large dipole moments, sometimes the lowest energy anion that can be formed is not formed by adding an electron to a pi star orbital here or a pi star orbital within the ring, but actually adding an electron into a region of space where the dipole moment of the molecule makes the potential especially attractive. So for example, I've shown here for the acetonitrile, the lowest energy orbital of the anion is really the electron existing in like a pocket sitting behind the methyl group, because that's the positive end of the dipole. And over here, I've shown the electron sitting over here on the side of the ring, not in a pi star orbital. And in the case of the acetonitrile, the electron is bound by 108 wave numbers. 8,067 wave numbers is an electron volt. So this is a fairly weakly bound electron, but it is bound, and it is the lowest energy state of that anion. So now here's a couple of references to early papers of my own group and other people who are dealing with these things. The point here, though, is that any molecule with a large dipole moment can bind an electron in this dipole binding motif, even if it doesn't have any low energy vacant orbitals. The dipole bound orbitals tend to be very diffuse spatially because the electron in them is very weakly bound. For dipole bound orbitals, to have an electron bound by, say, 500 wave numbers or 1,000 wave numbers would be a fairly strong electron binding. So these are weakly bound electrons. Now, because of that, their treatment theoretically requires specialized basis sets, which our group and others have been involved in developing. Very diffuse basis functions that are not centered necessarily on the atoms of the molecule. Another issue here is because this dipole orbital, this orbital right here, is big and fluffy and diffuse, it's highly polarizable. And as a result of that, the electron that's in that orbital has a very large dispersion or van der Waals interaction with the other electrons in the underlying neutral molecule. That is a very significant contribution to the binding of the electron is not just the electron dipole attractive potential, but also the dispersive interaction of the electron in this orbital with the other electrons in the molecule. This correlation energy dispersion interaction can be a very significant fraction of the electron binding energy. Now, in dipole-bound orbitals, as with most molecular anions, only one bound state is usually observed. Usually. If the dipole moment is large enough, you can have excited states of that are dipole bound. But the dipole moments in those cases have to be bigger than, say, 10 debis. Most molecules that have dipole moments in the 2-3 debye range bind only in the lowest electronically bound state, and the excited states are not bound. And the general trend is the larger the dipole moment, the larger is the electron binding energy. Okay, let's look a little bit more at these. Now, how do they measure these electron binding energies experimentally? Well, one way that has been done, and this is a reference to some of the work in this area, is to collide. For example, here we have an indole molecule with maybe one water molecule bound to it, or an indole molecule by itself, or maybe with two water molecules bound. And what the experimentalists have done here is to form Rydberg excited states of alkali atoms. For example, alkali atoms in Rydberg state n equals 5, 10, 15, 20, so forth. They collide these Rydberg excited atomic states with the indole, or indole with one or two water molecules attached. And when the excited Rydberg state is weakly bound enough that the electron can exothermically transfer onto the bound state of the dipole bound situation, then the electron will transfer and you'll form a species that you can detect in your mass spectrometer that will have the mass to charge ratio of, in this case, an indole with one water with an electron attached. It'll be negatively charged. So in this case, for example, they studied that you had to get up into about the 20th Rydberg state before an electron could be transferred directly over to an indole. But if there's one water molecule attached to the indole, you only have to get up into about the 7th Rydberg state before you start to form the indole water anion. So they can, by knowing these electron binding energies of the Rydberg states of the atoms, they can then infer the electron binding energy of the indole or indole water complexes. Now, where do these dipole-bound anions occur in systems that are of interest to all of us? Well, one place is in what's called charge transfer to solvent states of regular anions in, for example, water. So, for example, if you're studying iodide anion, I-, in water, and you do photo excitation experiments, and these are some studies done by Stephen Bradforth and Pavel Jungwirth in this reference here. You can excite an electron from the p orbital, the outermost p orbital of the I-, that's the orbital the electron's in anyway, and you can kick it out into the solvent, but the surrounding solvent water molecules may have, depending on their instantaneous positions, regions of space where the dipole moments of the water molecules might be pointing inward into this region of space and make it especially attractive for an electron to be there. And if there is such a pocket in the surrounding water molecules, then the electron could be kicked out of the iodide and into this pocket. That's what's called charge transfer to solvent, excited state in water. So you've transferred an electron from the I- into this pocket here. And this pocket is like a dipole-bound state because it has several water molecules with their dipoles all pointed inward toward the I- to then create in this region of space a place that is attractive also for an electron to be. This is another picture that's coming from this Bradforth-Jungwirth work that shows the I- on the surface of a water cluster with the electron attached over here. Now, there are possibly just clusters of water molecules themselves can have regions of space where, that is with no I- present at all, but you might have a water cluster. For example, here's water 45 from some studies that Peter Roski's group did. Water 45 cluster might at one time, as it fluctuates its motions around, present a region of space. Here it's on the surface of the water cluster where there's water dipoles pointing outward in a direction away from the cluster, forming a region of space where an electron could be bound, dipole bound. So here we have a surface bound ground state. And it turns out the water 45 cluster is big enough to have a strong enough dipole potential here that there's even bound electronically excited state. So here's like a P-shaped, first excited state. This is like the S shape, and this is like a P shape. So in these cases, you do actually have bound excited states. These dipole-bound anions for water clusters have actually attracted a lot of attention in recent years. A lot of the nice experimental work has been done by Mark Johnson's group in this field. And what they do is they take a water cluster anion, so for example, here's water tetramer anion, and they form it in their mass spectrometer in the gas phase, but they do it with a noble gas atom attached to it. For example, it might be an argon atom attached. Now, the argon atom doesn't do any chemistry. It's just sitting there, van der Waals attracted to that water tetramer anion. But what it does is allow them to carry out the following kind of experiment. They shine infrared light on this water cluster anion, and they tune the frequency of the infrared light, and they monitor in their mass spectrometer for the appearance of, for example, if they start with water tetramer anion with one argon present, they look for in the mass spectrometer signal the appearance of daughter anions that are formed that are just water tetramer anion with no argon atom attached. And the basic idea is that the water tetramer anion with one argon atom attached, if you excite at this frequency, you're exciting a particular vibrational frequency of the, and I think this is for a deuterated H2O instead of D2O instead of H2O. But anyway, if you excite this particular vibration of the water molecules in the cluster, then that water molecule vibration gets excited, and it then dissipates some of that vibrational energy to the other modes in the molecule, and the weakest mode is the mode that holds the argon atom onto the cluster. So the argon atom comes boiling off, it pops off. So by monitoring the appearance of the daughter anions as a function of the frequency of the exciting infrared laser, you can detect peaks of appearance of the daughter anions at specific frequencies where the vibrations of the parent anion cluster did their absorbing. So in the so-called action spectrum way, Mark Johnson's group has been able to get some really nice experimental data on the water cluster anions, several of them, and to vibrationally characterize them and therefore learn something about their geometry. Because once their vibrational spectrum is known, by then carrying out some electronic structure calculations on various putative structures, so for example, cyclic or quasi-linear structures of water tetramer anion, and then comparing the theoretical vibrational spectrum to the experimental vibrational spectrum, you can rule out, for example, the quasi-linear structure, because that spectrum doesn't look at all or very much like the experimental spectrum, whereas the spectrum of this cyclic structure here, the theoretical spectrum, tends to agree pretty well with the experiment, and therefore you can infer that probably what Mark has in his experimental sample that he knows is H2O4 minus, but he doesn't know its geometry, probably this geometry. So that's the kind of thing that one can do there. Okay, so let's now look at another example, and that is the example of what is called double Rydberg anions. This is another member of our family that's especially unusual. So these double Rydberg anions, here's the basic idea. Suppose you had an NH4 plus cation, or maybe you had H3O plus cation, or maybe you had trimethyl, actually this should be tetramethyl ammonium cation is what this thing should be that I want to talk about. So anyway, if you have yourself a closed shell molecular cation, there's no obvious low energy vacant orbitals for an electron to attach to. However, the overall molecule is a cation, so there's this attractive potential that I talked about earlier. So it turns out that these closed shell molecular cations, they actually can bind an electron not necessarily, for example, in an NH bonding orbital or anti-bonding orbital or an OH anti-bonding orbital or a nitrogen-carbon anti-bonding orbital. That's not where the electron goes. It's going into an orbital that essentially is around the entire positive site of the molecule, and these are called Rydberg orbitals. Now this has been known for a long time. Early spectroscopists like Hertzberg and others have studied these Rydberg states of, for example, NH4. You can put an electron into the lowest energy orbital of NH4 to form this state. You can put an electron into an excited orbital of the NH4 to form an excited state. There's many of them because those positive charges support a manifold of excited electronic states of the neutral. So there's a rich electronics pattern of energy levels of these Rydberg neutral molecules. But the double Rydberg anions come about in the following way. Every chemist knows if there's an orbital, you might put one electron in it, for example, to form NH4 neutral or H3O neutral. But what about putting two electrons in there? If that attractive potential is strong enough to overcome the repulsion of the two electrons in the same orbital, maybe you could actually form NH4 minus or H3O minus or tetramethyl ammonium minus is what that should be. Now, are there experimental cases where this is the situation? Yeah. Kit Bowen at Johns Hopkins University in the 1980s actually observed these double Rydberg anions, I think, for the first time. And what he was doing is he was studying, for example, the photodetachment spectrum of H minus, so just a hydrogen atom with an extra electron attached. And this is a measure of the electron binding energy as the intensity of electrons being ejected as a function of, if you will, photon energy. But he really was measuring electron binding energies, and he found that for H minus, the electrons bound by about 0.7 EVs. Everybody knew that. He thought that when you added an electron to, when you added an ammonia molecule to H minus to solvate it, that what would happen is you would form a species H minus solvated that would hold its electron more strongly than H minus. And indeed, he did find a peak in his spectrum where the electron was held more tightly than it was in the case of H minus. Excuse me. However, and this peak was at about 1.4 electron volts, something like that, electron binding energy. However, he saw a little tiny peak that had an electron binding energy of about 0.5 EVs, that is lower than the electron binding energy of H minus. So this led people, in particular Vince Ortiz was one of the first to do this, to look at the possibility that is there a species that is H minus NH3 in stoichiometry that is not H minus solvated, but has some other structure? that is NH4 minus. And it turns out that this species here, this so-called double Rydberg anion, that's really the NH4 cation structure with 2 electrons bound to it, is the species that gave rise to that little peak over there. So that's an example that, of the double Rydberg anions. Okay, now I'm going to close this session here, and we'll move on to the third section of the wonderful world of molecular anions in a minute.